Alright, folks, I want to continue to talk about lines. So, we did some exercises about how to draw lines and how to figure out equations of lines given some points, how to find the intersection point of some lines. So, we've done some good stuff that way. I want to talk about parallel and perpendicular lines now. So, well, we know what these mean in terms of geometry, but how can we relate that to coordinates and to equations and to algebra? So that's what we're going to talk about. So I'm going to write down two facts that are kind of fairly easy to prove. So the first one is that vertical lines are parallel. And the second one is horizontal lines are parallel. So that's pretty obvious. I don't want to go into too much detail about that since it's such a simple fact. But we know if we have two vertical lines, they're parallel. If we have two horizontal lines, they're parallel. That's pretty obvious. But what about lines that have some sort of slope, some diagonal lines or oblique lines? So that's what we're going to talk about now. So lines with some, and I'll say non-zero, which I'll talk about in a little bit, slope. Well, I want to show two things here. So it turns out that two lines are parallel exactly when they have the same slope. So again, remember this exactly when statement. This means an if-then statement in both directions. So this is saying if two lines are parallel, then they have the same slope. And it's also saying if two lines have the same slope, then they're parallel. So it goes in both directions. It says we're not missing any cases when we talk about lines with the same slope, them being parallel. There are no other cases for parallel lines, and vice versa. There are no sets of parallel lines that don't have the same slope. So we're doing kind of both directions here. So again, we have two results to prove. Let's do the backwards direction first. So let's say proof first. So let's do if two lines have the same slope, then they're parallel. And the way we're going to do this is we're going to do it by contradiction. We're going to pretend that there is a counterexample. So let L1 and L2 be two lines with the same slope that are not parallel. And let me be clear here. I want them to be two different lines. That's important to us. So they're two different lines, but they have the same slope, and they're not parallel. So the if part is true, that they have the same slope, and the then part is false, that they're not parallel. So we're doing proof by contradiction. We're going to show that if we pretend there's a counterexample, the world, in math anyway, breaks. So what does that mean? So that means that the lines have equations. Say for line 1, it's going to be y equals, let's call it mx plus some y-intercept. We'll call it b1 for line 1. And for line 2, y is going to equal, well, it's going to have the same slope, because remember that's what we said, that these two lines have the same slope, but they're different lines, so the only thing that could be different about them if they have the same slope is if they have a different y-intercept. Okay, so there are the equations of our lines. The other thing we have to mention here is that these aren't the same lines, so b1 and b2 aren't the same number, not the same real value. Okay, so what does it mean for these two lines to not be parallel? So since we assume that L1 and L2 are not parallel, so I use the parallel symbol and then put a slash through it, so they're not parallel, it means that they must meet at a point. Then L1 and L2 meet or intersect at some point. Let's call the point RS. So whatever values, the x value we call R, the y value we call S. If they're not parallel, they have to meet at some point. That's what it means to be not parallel. So this means that if we plug in x equals R and y equals S, remember R and S are just some numbers. This is the point where line 1 and line 2 meet. Well, we get equality. Thus, well, if we plug in the point RS, we get equality. So that says that S in line 1, S, which is the y value, equals m times R plus b1, since y and S is our y value, y equals mx, R is our x value, plus b1. And the same thing with line 2. And S equals mr plus b2. And you can kind of see what's going to happen here. The only thing that differs about these equations that both equal S are the b1 and the b2. So let's equate both, since they both equal S, they both equal each other. So let's equate both, let's say right-hand sides. We get that mr plus b1 equals mr plus b2. Subtract mr from both sides, and we get that b1 equals b2. But that's a problem, because we said originally that b1 and b2 were different numbers, since L1 and L2 were different lines. Remember that? Remember we said b1 and b2 were different. That's how we set these up. These guys are different lines. But we showed down here that b1 equals b2. So this contradicts b1 not equaling b2 above. So there's no way that b1 can equal b2 and not equal b2 at the same time. So our mathematics broke. And since we get this contradiction, it must mean that there must be no counterexamples. Thus, there are no counterexamples. And the theorem is true. Great. So we have one direction. We have that if two lines have the same slope, then they are parallel. That's great. The other direction, it's a little bit more technical to prove, not too much more technical, but it involves using some of our geometry skills. Okay, so let's do the other direction now. So let's assume, Oh, I want to do that in black. So assume that L1 and L2 are parallel. And we need to show that they have the same slope. So that's our goal. So let's draw it. Let's draw L1 and L2. So let's say this is L1 in black, and in blue I'll draw L2. Here is L2, and these guys I'm going to mark as parallel. We know these guys are parallel. So what we're going to do is we're going to draw some vertical lines between them to make a parallelogram. Once we have that parallelogram, we can start arguing about the slopes of L1 and L2. So let's go ahead. So let's pick a point. Let's call it x1, y1, and another point, x2, y2, and we're going to draw vertical lines. And I guess I should say we're going to draw two. Sorry, not vertical lines. These are obviously horizontal lines. When I've been saying vertical all these times before, I mean horizontal. Sorry, guys. Okay, and remember, horizontal lines always have the same y value. So I'm going to draw the horizontal lines in green. So I'm going to draw this horizontal line. And so it ends up at this point. And this point here, well, I don't know the x value, so we'll give it a new name, x3. But I know it has the same y value as any other point on the horizontal line, so y1. Similarly, up here, I get this horizontal line. It has x-coordinate something, I don't know, I'll call it x4. And y-coordinate, well, y2. It's going to be the same y-coordinate as any other point on a horizontal line. And here's one point on my horizontal line. And I can say since these two lines are horizontal, they are parallel. So let me put some parallel markings on these guys. Maybe I'll do 2 just to indicate that they're parallel with each other and no other lines. So let's talk about more specifically what we need to show now. Now we have 2 points on each of the lines L1 and L2, so we can kind of figure out the slope of both of these. So let's scroll up. So the slope, I'll write m of L1. The slope of L1 is, of course, the change in y over the change in x. So we can write it like this. So our change in y is going to be y2 minus y1, and our change in x is going to be x2 minus x1. So that is y2 minus y1 over x2 minus x1. Any 2 points on our line can give us our slope. And the slope of L2, of course, again, is change in y over change in x. Well, the y-coordinates are the same. It's going to be y2 minus y1. But now our x-coordinates are x4 minus x3. So the only difference between the slope of our first line and our second line are these denominators, x2 minus x1 and x4 minus x3. So if we can show that x2 minus x1 equals x4 minus x3, we have shown that the slopes of both lines, L1 and L2, are the same. So that's our goal here. So the way we're going to do this, let me label these points up here. Let me scroll back up and label these points. Label them in, we didn't use red yet. Call this point A, I'll call this point B, I'll call this point C, and this point D. And basically what we want to show now, we want to show that line AC has the same length as BD, because AC's length, well, it's just the difference in the x coordinates, just like a number line. So this length is x3 minus x1. Or maybe I'll do that in green, actually, to be the same color. The length here is x3 minus x1, and the length above is x4 minus x2. So if I can show they're the same, then that will help me prove that the slopes are the same. And this reminds me of a problem you did in lab, most likely, and that is if you draw a diagonal line, imagine that that's a straight diagonal line. Maybe I can draw it a little bit straighter. That's a little bit better. Then, via the arguments we've already seen in lab, we know that they are indeed the same length. We know that triangle ABC is congruent to triangle DBC. So, via the arguments from lab, we know that triangle ABC is congruent to triangle DBC. And so what do we get out of that? Oh, that's not what I wanted. So what do we get out of that? We get that line, oh, I have this correspondence incorrect. Sorry, folks. This should be A, B, C, and D, C, B. And from this correspondence, we get that line segment AC and DB are the same length. So bicongruent triangles we know that line segment AC equals line segment, not A, sorry, DB, which tells us exactly what we want. So it tells us, let's scroll back up. Well, it's not exactly what we want. Sorry, it's almost what we want. It tells us that x3 minus x1 is the same length as x4 minus x2. So we know that. And what I'm going to do here is I'm going to solve for one of these guys, let's say x3, and then see what happens. So, let's add x1 to both sides. We get x3 equals x4 minus x2 plus x1. Now, remember, we wanted to show that x2 x2 minus x1 equals x4 minus x3. So let's consider x4 minus x3 and show it equals x2 minus x1. So let's sub in for x3. So subbing in, we get that x4 minus x3 equals x4 minus, and now, well, x3 is the same as x4 minus x2 plus x1, which is the same as, well, let's expand that negative to all the terms in the bracket. x4 minus x4, minus a minus is a plus x2, minus and a plus is a minus x1. Look at this, our x4's cancel, so we get that this equals x2 minus x1. So we've shown that, so x2 minus x1 equals x4 minus x3. And remember from above that showed that the slope for the first line equals the slope for the second line. And we're done. That's what we wanted to show. So both these parallel lines, L1 and L2, have the same slope. So that's pretty cool. So whenever we see two lines with the same slope, we know they're parallel. And when we know we want parallel lines, we just want them to have the same slope. So we get both directions. Just a quick note about perpendicular lines. So I'll just write this as a fact. There is a proof here, and I'll point to the place in the book you can look it up. The argument's a little more complicated than what we just shown. So I'll leave it to you, if you're interested, to have a look at that. But the fact is that two lines are perpendicular. And let's give those lines names, I guess. Let's say they're L1 and L2. Exactly when, so remember this goes in both directions. So exactly when the slope of L1 is the negative reciprocal of the slope of the second line, L2. Or in other words, if you multiply the slope of L1 and L2, you get -1. Let me just give you an example. So if ML1 was 2/3, then for a perpendicular line, the slope of L2 would be the negative reciprocal. So you flip the fraction, so 3/2, and you've changed the sign. So it was positive, it becomes negative. And you can check that 2/3 times -3/2 does indeed equal -1. And I will say, the proof of this fact is in Appendix C of the book. So have a look there. And it's the same idea as the parallel proof, except it's a little more involved. So that's all that's going on there. Let's do a quick example to finish. So let's show Or let's do this. Find a line perpendicular to the line y equals 2x minus 1 that passes through the point I don't know, let's do 3, 7. That will do. Okay, so let's kind of draw the situation first, just so we get some geometric intuition. So there is our xy axis. We have the line, let me put in some markings here just to help us out. We have the line 2x minus 1. I know the y-intercept is minus 1, so I'll plot that point. And then say I'll plug in 1, and if I plug in 1 into 2x minus 1, I also get 1. So I get the point 1, 1 as well. So both 0, negative 1, and 1, 1 are points on the line y equals 2x minus 1. So let's graph these. Or graph this line, I guess. So there's a sketch of it. And we needed to pass through the point 3, 7. I'll need to make this a little bit bigger. That's okay. So it's going to pass through the point 3, 7, 4, 5, 6, 7. So our line is going to pass through this point all the way up here. So it's going to look something along the lines of that. And it looks like our y-intercept is going to be quite large. It's going to be definitely above 7, maybe something like 11, 12, 13, somewhere around there. So we can take a guess at what the line looks like. And again, the slope, well, it's a negative slope since it's sloping down to the right, and it looks like it's sloping at a less steep angle than y equals 2x. In fact, we'll find out that it's definitely negative a half, because that's a definition or the fact for a parallel line, or for a perpendicular line. So there's our sketch. So let's let L2 be the perpendicular line. Then the slope of L2, well, that's just going to be the negative reciprocal of 2. 2 is the same as 2 over 1, so we'll flip the fraction, take the reciprocal, becomes 1 over 2, and we'll make it negative. So we know the equation is going to be y equals negative a half x plus some y-intercept. So we just need to solve for that y-intercept. We know a point on the line. We know, in fact, 3, 7. So let's plug in 3, 7 to find b. So let's do it. So we get, well, y equals 7. That is negative 3 halves times 3 plus b. And we just solve for b. So this is going to be, I'm going to change things to fractions over 2. That'll just help us out. 14 halves equals, well, negative 3 halves times 3, or 3 over 1, you can check, is negative 9 halves plus b. Add 9 halves to both sides. 14 plus 9 is 23 halves equals b. And as a mixed number, if you like, that is 11 and a half equals b, or 11.5. So the equation of L2 is y equals negative a half x plus 23 over 2, or plus 11 and a half. And that jives with the diagram or the sketch that we've drawn. So that's great. And I'll leave us an exercise for you guys. And it's going to be very similar to a problem that we did. So find the intersection point of these two lines. All right, so that's all I want to talk about today regarding parallel and perpendicular lines, and we're going to move on to a new topic.